In today's cultural and architectural landscapes dominated by rapid change and globalization, there are a handful of monuments and buildings that stand out. They have acquired a status that goes beyond their mere form or purpose. They have become the symbols for their cities, their time, their cultures. Its long history has awarded the City of London many remarkable structures. But together with Big Ben, the famous clock tower flanking the Houses of Parliament, the most recognized symbol for this city is the Tower Bridge. Revered by Londoners, loved by tourists, the bridge on the eastern end of London's inner city is perhaps the most photographed bridge in the world.
Tower Bridge is a combination of marvellous feats of engineering with a magnificent, monumental Victorian architectural structure. So the two coming together are much more than the sum of the parts, and this is what gives this great bridge landmark quality.
Tower Bridge was called the Wonder Bridge because of the way it was automated and opened to let ships pass through.
It's only when you see the machinery and you understand how it worked that you appreciate the enormity of what it was for the people that designed it in the 1890s.
Although more than 100 years old, Tower Bridge is a relative newcomer among London's bridges. The history of bridging the Thames goes back almost 2,000 years. Invading Roman armies constructed the first timber bridge near their settlement Londinium around 70 AD. In 1176, construction began on the first stone bridge across the Thames. It would be the city's most famous landmark for centuries, London Bridge. Completed in 1209, the long-awaited bridge quickly became popular, not only as a means to cross the river, but as a place to do business, even as a place to live.
The original London Bridge was quite a remarkable bridge, and it went through a whole range of evolutionary stages, from being just a plain road bridge to then having houses built on it. It had a chapel built on it. It had a gatehouse. The bridge didn't have a regular pattern of arches. It was very irregular. And the reason it was irregular is when they built it, they built the piers on parts of the riverbed that were hard. They poked the bottom with large poles, and where it was solid, they built a pier.
It acted actually as a Thames barrier. It was such an obstruction to the river that at all states of the tide, there was a 4 to 5 foot difference in level across the bridge.
The drop in water level created by the bridge made it virtually impossible to go upstream, even for boats small enough to pass through the narrow arches. And even going with the current was a risky undertaking that became known as shooting the bridge. For 6 centuries, London Bridge remained the only way to cross the Thames other than by boat or ferry. At the dawn of the industrial age, trade boomed in London. England was becoming a major colonial power with territories and trade interests around the world, and an increasing flow of goods arriving at her ports. Beginning in 1729, a number of new bridges were erected in London and neighboring communities, but all were west or upstream of London Bridge. In the early 19th century, London's population passed the million mark. It would quadruple within 50 years, making London 4 times as populous as Paris or New York City. In 1831, a new London Bridge was completed right next to its crumbling predecessor, which was torn down after the new crossing was taken into service. The new bridge did little to ease congestion.
There was, of course, no other bridge to the east of London Bridge. And to the east is where a lot of the city was starting to grow, so that more than 1 million people lived to the east of London Bridge, and that was the only way that they could cross the river. So it was jam-packed full of horses and carts and people and hand carts and animals all being driven across. So there was a real desperate need to have some other river crossing.
Though the need for a crossing east of London Bridge was obvious, building another bridge seemed out of the question. Because to the east of London Bridge began what is called the Pool of London, an undistinguished stretch of river barely 1.5 miles long. Today, the few remaining warehouses that line the Pool of London house loft apartments for affluent Londoners. In the 1800s, they were at the center of the world's busiest port, with a turnover of up to 300,000 tons of goods per week. At times, more than 20,000 workers were employed on the docks and wharves.
If you ever see the photographs of the upper pool of London with all the ships in it, you could almost walk across the river on the shipping. There was that many ships in the upper pool.
Trade companies that had invested large sums in the docks were among the strongest opponents of a bridge to the east.
To have built an ordinary bridge across the river at the point where Tower Bridge is would have destroyed the docks further up, because most ships were sailing ships, so none of them could have got through. So all those docks would have fallen into disuse.
Another group fiercely opposed to the bridge project, to any bridge project in fact, were the owners and operators of ferries across the Thames. Facing such opposition, a bridge downstream from London Bridge seemed unlikely. Many of London's bridges were privately owned and levied tolls from pedestrians and vehicles. Needless to say, these tolls were not very popular with the general public. In the late 1870s, the Metropolitan Board of Works, a governmental body for the County of London, spent about £1.4 million to purchase 11 bridges and make them toll-free crossings.
The Metropolitan Board of Works, London's central government, had used ratepayers' money to buy all the London bridges from the companies across the Thames in central London and free them from tolls. And once that had been done, people living east of London Bridge made lots of demands for their money to be used to give them a crossing.
In addition to pressure from the public, the docks and wharves themselves, the same interests that opposed a bridge in the past, were the cause of an increasing need for a new crossing. It had become apparent that the vast quantities of food and merchandise arriving at the docks had to be transported through the congested streets of London and across London Bridge, where they were often delayed for hours.
It was the docks that changed everything. Here was a great city investment of capital into a wet dock system down below London Bridge, and getting access for goods in and out of London and across the Thames became a very important issue. Not so much for social reasons for the people, except it provided employment, of course, in the docks.
With interest in a new crossing east of London Bridge renewed, it was now up to London's architects and engineers to develop ideas for this much-debated project. The location of Tower Bridge, right next to the historic Tower of London, was determined in 1876. The Corporation of London had created a special bridge or subway committee to select the site and evaluate proposals for a new Thames crossing east of London Bridge. After it was clear where the new bridge should be, the main challenge facing all the engineers and architects was how to get vehicles and passengers across the Pool of London without impeding shipping traffic. In 1879, the Metropolitan Board of Works presented 3 designs by their own chief engineer, Sir Joseph Bazalgette. Out of the 3 proposals, one clearly stood out. It was a concept for a steel bridge, an elegant design that leapt across the Thames in one single elongated 850-foot arch. A horizontal roadway was supported 65 feet above high water level. The approaches consisted of one long straight approach to the north side and one spiral approach to the south. Crucially important to this and all other bridge proposals was the gradient of the approaches. The gradient reflects the relation between the height and the distance to reach that height, in this case 1 to 40.
The horse was the motive power, either for omnibuses or cabs or freight carrying carts. So you always had to look at the gradient.
Horses were a very big issue 100 years ago because that was the means of transport. Cargo drawn by horses and carts clearly is best if it's drawn on completely level ground.
The inherent problems in Bazalgette's designs that led to their eventual rejection were problems that would haunt all fixed bridge proposals. To clear shipping traffic, the bridge had to cross the Thames at a fairly high level, at least 100 feet above the high water mark. But to get traffic to such a high level, the approaches would have to be extremely long in order to accommodate horse-drawn traffic. The room for approaches, however, was very limited.
The amount of land take, particularly on the City of London side, would have meant demolishing very expensive property and was just ruled out on economic grounds rather than on technical feasibility.
One design attempted to solve the problem by installing large elevator platforms on each side of a high-level bridge.
You entered a lift at one bank, went up into a high-level lift, crossed the bridge, and then entered another lift and went down the other side. That would have been fine, but if you consider that now we have 40,000 vehicles a day crossing the bridge, no way could it have coped with the flow, and not even in Victorian times.
Clearly, to solve this dilemma, the bridge builders needed a better concept. 2 years prior to Bazalgette's proposal, designer F.J. Palmer had suggested a so-called duplex bridge.
You had the bridge designed so that one part of it opened so a ship could enter, and you still had a continuous road. Then the gate was closed, which also contained a road behind the ship, and the other side opened so the ship could then pass through and the road traffic would be maintained. But that was considered to be too complicated and also not practical because of the high running speed of the tide. It would have been difficult to have moored the ships and then let them release again.
Nevertheless, with a fixed bridge out of the question, the duplex bridge design was a step in the right direction. The bridge would have to be at a low enough level to allow for approaches of reasonable length and gradient. And it would have to be movable to let ships pass unhindered. Of the many proposals brought forward between 1877 and 1885, several took their cues from this idea, sometimes with rather unconventional results. One design had 2 swing spans pivoting around 2 massive towers and a short tunnel with elevator access to be used when the bridge was open. Another truly bizarre design was not really a bridge at all. It was a pontoon-like road segment, 100 by 300 feet in size, that would roll across the Thames on a half-dozen piers fitted with rolling pins. The designer estimated his rolling bridge would make the trip across every 6 minutes, always leaving a large portion of the Thames open for ships to pass. In 1884, one proposal emerged as the frontrunner.
Why was this design chosen when there were some very good designs amongst the others? And the reason I think it's quite simple is that the Corporation of the City of London had their own in-house city architect, Horace Jones, who had sketched out a rough bascule design, a slightly fanciful, whimsical design. But they then decided that they would fund the design and construction of the bridge, which of course means that he who pays the piper calls the tune.
Horace Jones, the man with the inside track, had submitted his design for a bridge in 1878. But Jones was not only competing for a winning tower bridge design. As city architect, he was also involved in evaluating the many proposals. Beyond his political advantage, Jones' design showed some merit in addressing the problems facing a bridge across the Pool of London. His bridge consisted of 2 brick towers, resting on massive piers and accessed via steel suspension bridges from the shore. Between the towers, an arch supported 2 chain-drawn bascule leaves, wing-like bridge segments that could be raised much like medieval drawbridges to let ships pass. John Wolfe Barry, son of Sir Charles Barry, the designer of the Houses of Parliament, was assigned as the engineer to work on the bridge with Jones. He soon helped eliminate a substantial flaw from the original design. The central arch demanded that tall-masted ships pass dead center. Any deviation from course could result in a collision with the span. Wolfe-Barry replaced the central arch with a horizontal, high-level dual walkway. Pedestrians unwilling to wait for the bridge to close would have the option of riding up a tower in an elevator, crossing the footbridge and descending on the other side.
In purely reductionist engineering terms, you don't need the towers because you can operate the bascules from the piers and have a low-level roadway without having towers. But once this idea that you should maintain a free passenger flow across the river, even when the shipping was passing through the bridge, dictated, of course, that you had to have an upper bridge, and that bridge had to be quite high to clear the masts of sailing ships.
The modified design would provide a clearance of almost 140 feet between high water level and the upper footbridges when the bascules were raised. The support of the suspension chains and the central walkways raised another doubt about Jones' original design. Towers built from brick as he had envisioned would not be strong enough to withstand the mechanical forces imposed on the bridge. But the choice to include brick towers into the design was prompted by demands to give the bridge a look that would not clash with that of its neighbor, the 800-year-old Tower of London. Even Bazalgette, when designing his fixed steel spans, had sought to make his bridge blend with the tower by adding quaint medieval details to approaches and piers. After the public had marveled at the filigreed structures made possible by building with iron and steel, a sort of aesthetic backlash had occurred and affected a change of architectural taste in Victorian England.
There was a period in the middle of the 19th century when the great railway engine sheds and structures like the Crystal Palace, the site of the Great Exhibition in Hyde Park, were built out of exposed iron and steel. And it was towards the end of the century that there was a reaction to this, and people wanted to actually cover up the steelwork and the ironwork and see that as a skeleton, and then have artistic decoration and stonework on the outside.
To accommodate both structural needs and public taste, a crucial and far-reaching change was made to Jones' original design. The bridge and the towers would be built as a steel frame and then covered to modify its appearance. White Cornish granite and Portland stone were chosen for the cladding. Aside from its decorative purpose, the masonry would also protect the steel from the elements and subsequent corrosion.
I think most engineers would have preferred a structurally honest, visible system. The aesthetic of this is all wrong, and it came in for a great deal of criticism. And here, the actual structural form was a visual lie. It looks like stone towers, and in fact, the structural steelwork inside, the engineering part rather than the stonemasons part, was the piece that was doing the work.
After a long debate, Parliament set forth the dimensions of Tower Bridge and conditions for its construction in 1885. The cost for materials and construction was estimated at £750,000. Finally, on June 21, 1886, the Prince of Wales performed the groundbreaking ceremony. Shortly thereafter, a workforce of more than 400 men started Phase 1 of the project, the construction of the largest piers in the world. They would soon get a taste of the difficulties ahead. The unique structure of Tower Bridge rests on two enormous piers, 180 feet long and 70 feet wide. Each of the piers has to support a weight of 70,000 tons. The pier's size was not only dictated by the fact that they had to support the towers, they also had to have room for engines and counterweights.
The piers that you might think are solid are in fact hollow. When you see the bridge go up, this weight descends into that counterweight chamber, which is of cathedral dimensions.
To support the bridge structure and withstand water pressure, but also to survive the chance encounter with an errant ship, the pier's walls had to be extremely strong. They would be 10 feet thick in the weakest spot on the side, and a sturdy 22 feet at the up and downstream corners. Work on the foundations and the piers began in 1886. When they were completed, they would be the largest piers in the world. To lay the foundations and build the piers, workers sank caissons onto the riverbed. These were large metal boxes, 57 feet tall, and open at the top and at the bottom. The caissons penetrated the riverbed 26 feet deep into the underlying layer of clay. The water was pumped out and a layer of gravel removed. Then the lower part was filled with concrete to create a foundation. The upper caissons, which were eventually taken out, formed a metal wall that held out the water while the piers were built from brickwork and granite. Unfortunately, the piers could not be built in one piece due to restrictions by the river authorities.
The Thames conservators who managed the river made a very stringent restriction on operation that you had to keep 160 feet clear between these two caisson walls at all times during the construction. Now the spacing of them meant that you couldn't build the two piers completely in one caisson at a time. You had to split the pier longitudinally, build one half of it, and then move the caisson over. An expensive and time-consuming business.
So time-consuming that it took 4 years just to build the piers, almost as long as the projected schedule for the entire project. After the piers had been completed, construction could finally begin on the steel superstructure, beginning with the 120-foot steel frames for the main towers.
Each of the towers comprises of 4 octagonal columns. They support the weight of the suspension bridge at the top and are linked together by the walkways.
Amazingly, the bridge's entire steel structure, including the massive tower columns, was made up of thousands of relatively small steel plates and beams, weighing no more than 5 tons apiece.
The stipulation was that the cranes could only handle a 5-ton piece at a time. The pieces had to be manageable.
To piece together a rigid structure of this size, the builders needed a reliable technique to join the steel segments. They chose to use rivets, and 3 million of them were used to fasten everything from the tower frames to the bascule girders and suspension chains. Once the tower's main frames had reached their intended height, the difficult task of building the footbridges began. The latticed box girders supporting and enclosing the walkways were cantilevered out from both towers simultaneously. It was a slow and difficult process as the girders inched toward each other. Despite the fact that all the pieces had been test-fitted in advance, some doubts remained that they would meet and match as intended.
Because the piers would settle into the river very slightly, and with the riveting system is not as good as nuts and bolts in terms of register, and they had no means by laser beams to measure how accurate they were. There was a bit of pray and hope, I think, that when they got to the middle they did find that it all lined up properly.
When the walkways of Tower Bridge finally joined above the Thames, they turned this work in progress into the first bridge ever downstream of London Bridge. With the walkways completed, attention focused on the 2 suspension bridges from the riverbanks to the towers. On top of the temporary wooden bridges that spanned the Thames between the piers and the riverbanks, large wooden trestles and scaffolds were erected, leading upward to the main towers and the smaller abutment towers. On these trestles, workers assembled the massive stiffened suspension chains, weighing as much as a ton per foot. They were led from the main towers over the abutment towers to shore, where the chains were anchored in huge 30 by 50-foot concrete blocks. While the construction of the towers and the suspension bridges was challenging, steel suspension bridges had been built on a larger scale since the 1830s. At the center of Tower Bridge's unusual design was the double-leaf bascule bridge. No one had ever attempted to build a movable bridge of this size. The bascules, French for seesaws, are the movable bridge spans balanced with a counterweight. Each of Tower Bridge's bascules would weigh 1,045 tons. When these enormous spans were assembled, restrictions to keep the waterway clear of obstructions made it necessary to adopt an unusual mode of construction.
When the bascules were made for the bridge, because they didn't want to impede the river traffic, the girders were put in the upright position, and the work was done upright, even down to putting the wooden blocks, which were going to be the surface of the bridge, in place with the bascules in the upright position.
With most of the steel work in place, it was time for the stonemasons to go to work. Despite the fact that the bridge structure is supported by steel frames, the designers opted to use massive blocks of a special granite instead of thinner tiles for the cladding. This nod toward solid construction weighed in at more than 30,000 tons for masonry alone.
The white stone is called Portland stone, and the reason it's called Portland stone is it actually comes from a place called Portland, which is on the Dorset coast. It's a form of limestone, and it's very good for its hard-wearing properties, and it's also relatively easy to carve. So that was a stone that was used to carve into the ornate patterns that you see on the bridge.
The bridge's original architect, Sir Horace Jones, had died in 1887. Too early to even see the foundations of his last work completed. In his place, his assistant, George Daniel Stevenson, took over the project's architectural aspects and added some alterations of his own. Stevenson changed the original red brick facade to a white stone and granite look, and modified windows, walkways, and parapets. As the outer structure and the bridge spans took shape, a different kind of construction work was conducted on the inside. In cavernous chambers and engine rooms, an ambitious engineering project was underway. Workers installed magnificent machines that would use fire and water to hopefully bring Tower Bridge to life. When the builders of Tower Bridge pondered the various power systems that might drive their bridge, they knew every one of their choices would have to hold up to one key requirement: absolute reliability. The project had prevailed against strong opposition because they had promised that river traffic would not be obstructed. Nobody wanted to be responsible for failing machinery that could turn a movable bridge into a barrier in the middle of the world's busiest port.
When it was proposed that Tower Bridge should open by means of two bascules, there was a lot of derogatory comment that would these flaps always work, and they were talked about as flaps.
Machine failure was not the only concern that the engineers needed to address. The collapse of Scotland's Tay Bridge due to high winds in 1879, in which 75 people had died, was fresh on the minds of government regulators when they decreed that bridge structures should be able to withstand wind pressure of 56 pounds per square foot. Despite the fact that a wind of such strength would be highly unlikely within the City of London, engineers had to make sure that their bascules would close even if a wind of 87 miles per hour blew directly at them. While in theory several means of moving a bascule bridge were available, including hand-operated cranks, the necessary high gear ratios would make most bridge lifts too slow to be practical.
Once you've decided on having a lifting bridge, then the immediate technical question is, how are you going to achieve that? I suppose the greatest engineering technical feature of the bridge has to be the use of hydraulic power.
Hydraulics, the science of fluids in motion, was not new to the 18th century. Water-driven mills and pumps had been in use for centuries, but it was not until the industrial age and the invention of steam engines that water could be pressurized and accelerated at much higher rates than its natural flow. England was at the forefront of hydraulic engineering. In fact, in 1882, only 4 years before construction on Tower Bridge began, London had installed a system of hydraulic pipes that delivered pressurized water through street mains to workshops and office buildings, where it could be used to operate machinery, cranes, or elevators. To build the biggest hydraulic machine of its time, John Wolfe Barry enlisted the services of Sir William Armstrong, one of the pioneers in the field.
William Armstrong was an inventor, he was a scientist. His own home had any number of hydraulic embellishments. You know, he could move his flower pots in his conservatory, he could turn his spit hydraulically.
The hydraulic system Armstrong and Barry developed would drive the bridge until 1976. It was powered by 2 pairs of coal-fired boilers and 2 steam pumping engines, situated in the main engine room under the southern approach.
The engines themselves were very powerful. At the time they put out 360 horsepower. They weigh overall about 40 tonnes. The flywheel on itself probably weighs about 12 tonnes. Flywheel itself is to maintain momentum of the system so that when a bridge lift was required, it could instantly speed up, didn't have to start from scratch.
While 360 horsepower may not seem much in the age of high-powered combustion and jet engines, in the 1890s, these were among the most powerful engines available. The steam engines pumped out water at a pressure of 750 pounds per square inch. This pressurized water would be driven into 6 accumulators to store energy for moving the bridge. The accumulators were essentially vertical metal tubes. 2 were housed near the machine room in the southern approach, and 2 in each of the piers. A huge piston weighing 100 tons, as much as 2 battle tanks, acted as a pressurizing weight on top of each of the accumulators. The steam engines forced the pressurized water into the accumulators, pushing the pistons 35 feet up. Then, valves at the cylinder base were shut to prevent backflow, and the piston weights kept the water under pressure until needed.
When a bridge lift was required and ready to go, the engine driver would open up a valve which allowed the hydraulic water through the pipework, up over the bridge, and down into machinery rooms on the bridge and into the engines.
There, the force of the water would activate the engine's pistons, which in turn began to move the crankshaft. The motion from the crankshaft turned a system of gear wheels, which locked with toothed quadrants on the back of the bascules and moved the bridge. To decrease the drive force needed and to take stress off the gears, the bascules were balanced. By this simple measure, the driving machinery does not have to move the entire weight of the bridge leaf. It basically tips the balanced bridge in the direction it is supposed to go.
The white section of the bascule we can see above my head is the balance weight, which is the rear end of the bascule, if you will. And that's the shorter section of the bascule. The blue section is just the supporting structure for the bascule.
As the bridge is readied for a lift, hydraulic locks at the rear of the bascules are released. While the bridge swings upwards, the enormous counterweights descend into the cavernous 40-foot-high bascule chambers hidden inside the piers. To ensure reliable operation at all times, the hydraulic system was equipped with several levels of backups. Each of 2 twin Lancashire boilers could have provided sufficient power to drive the steam pumps. 2 pumps were housed next to the boilers. Again, each had enough power to pressurize the system. The hydraulic engines which turned the water pressure into the gear movement that drove the bascules were housed in pairs inside the machine rooms. Each of the engines could raise or lower the bascule by itself. In addition, each engine room was duplicated inside the piers.
It was built with considerable redundancy, so each of the bascules could be raised by one of 4 engines. So there were 8 engines altogether, and only 2 of them were required to raise the bridge.
As a final backup, the bridge was connected to London's new hydraulic main system, from where it could draw pressurized water on the off chance that all of its pumps and accumulators would fail. Installation of the many components of the hydraulic system of Tower Bridge took almost 4 years, from 1890 to 1894. After 8 long years, the structure of the bridge was finally complete and its hydraulic system operable. Almost £1.2 million had been spent on its construction, about $120 million in today's money. Now the latest and most impressive addition to London's bridges was ready for service. And a royal welcome. More than a century ago, on the last day of June 1894, the warehouses along the Pool of London were adorned in flags and banners. Hundreds of thousands of spectators lined the embankments and crowded the Thames in everything from barges to rowboats. The more fortunate waited in stands along the approaches, while an honor guard lined the length of Tower Bridge in expectation of the Prince and Princess of Wales. The royal cavalcade arrived at noon, and the prince stepped up to a silver cup on a pedestal, a switching device installed for him to raise the bridge. The heir apparent turned the cup, and nothing happened.
There is a story goes around that the only time the bridge failed to raise was on the opening day when the Prince of Wales turned the lever and the bridge didn't actually open. In actual fact, what happened was there was a time delay between him moving a handle, which was doing virtually nothing, to the guys that were driving the bridge actually lifting it.
After a few moments of anxious waiting, the bridge drivers finally received their signal, and under roaring cheers, the bascules lifted to let the first ship, the HMS Landral, pass. With the festivities over, the bridge could settle into its new role. A dual role, as it soon became apparent, as both a hard-working bascule bridge and a landmark for the City of London. Tower Bridge's ascent as a symbol for the city was almost instantaneous. Visitors to London flocked to the new Wonder Bridge, as it was called, eager to observe the bridge in action. Most people were undeterred by an ongoing debate about the bridge's appearance. The trade publication The Builder blasted the design only weeks after the opening, acridly remarking, "We decline to waste any plates in giving illustrations of the so-called architecture." The observation by the Building News that no real art can tolerate a casing was gentle by comparison.
People felt that it would have been much better had the engineering skeleton of the bridge shown through so that you saw the steelwork, and they felt that it was a sham to have covered it with baronial style architectural stonework.
It was innovative in the use of the steel, but then they covered that up, as though they were ashamed of it, with stone to match the tower. You have this sort of throwback to almost a Disney-like approach in making it look like a tower or a castle which it sat alongside.
The discussion about the Tower Bridge's Gothic exterior was only a minor concern to the people who used it and those who operated it. In its first year of operation, an average of 8,000 horse carts and 60,000 pedestrians crossed the bridge each day, with an average 17 lifts for shipping traffic. According to the Act of Parliament of 1885 that allowed Tower Bridge to be built, shipping would always have the right-of-way and never be impeded. To facilitate this, the bridge had to be operational 24 hours.
84 to 90 people used to work on the bridge. That was all trades. That was stokers in the boilers and people working in the workshops, the bridge drivers. Each of the machinery rooms was manned 24 hours a day.
Just in case a boat got stuck under the bridge, Tower Bridge had its own tugboat on permanent standby. In stables under the southern approach, the bridge also had a contingent of horses, a sort of 19th century tow truck.
The bridge did own additional horses to assist heavy carts across the bridge or to remove obstacles like a horse that might have died on the bridge, and that could delay a ship. There are references in the old incident books to horses having dropped dead in the middle of the bridge.
For all the traffic that went across and under the bridge, one component that had been a major factor in the bridge's design was scarcely used, and then not always for the purpose intended.
When the bridge opened, people were so fascinated by watching it lift that they didn't bother to use the high-level walkways as a means of going across. They used them much more for entertainment, perhaps in an afternoon going and having a walk on the walkways of Tower Bridge. It was a meeting place.
Meeting places they became, particularly for lonely Londoners out looking for love.
In those days, we were a 24-hour operation, and the ladies of the night used to come and ply their wares up there as well. And this wasn't thought by Parliament to be very good for the image of the bridge.
Another attraction that Tower Bridge seems to share with many famous bridges is its appeal to those contemplating suicide. While today the walkways are sided with double-glazed windows, there was no such protection when the bridge opened. On numerous occasions, jumpers would climb through the latticework and leap 140 feet to their deaths.
Right from the very word go, people would climb the stairs to the walkways and commit suicide. So in about 1908, they actually passed an Act of Parliament which said that the walkways must be closed, and they remained closed until we became a tourist attraction in 1982.
During World War II, German bombers rained destruction onto the City of London. Miraculously, Tower Bridge was unscathed by the London Blitz. It is widely believed that German bomber pilots preferred to keep the landmark intact, to use it as a marker for their bombing runs. After a brief resurgence of shipping traffic in the post-war years, the demise of the Port of London posed a different threat to Tower Bridge. The passage of ocean-going ships that required bridge lifts steadily declined in the 1960s, leading to a discussion whether Tower Bridge should become a permanently fixed bridge. In 1970, the Corporation of London decided to keep Tower Bridge as a moving bridge, but to replace the old steam-driven hydraulic system.
The number of ships coming up was such that it didn't warrant having the bridge operational 24 hours a day, and therefore some other means of driving the bridge had to be found. The steam engines, of course, had to have continuous attention, and the idea was to change them to an electric motor which could easily be switched on and off.
After more than 80 years of trouble-free service, the steam engines were replaced by electric motors powering an oil hydraulic system. The bridge retained a large part of its old machinery, which is now a major attraction in its own museum. And if the current bridge master has his way, it may someday be taken out of retirement.
It's one of my long-term ambitions to get them running on steam again, which I think would be tremendous. We would have had a dual system probably with an electric motor.
Even though more mundane machinery now does the work, and ships need a 24-hour notice to have the bridge lifted, Tower Bridge still opens up for shipping as it has for more than a century.
Stand by bridge staff, about to stop road traffic.
And road traffic just has to wait, no matter who is in the car.
We actually stopped Bill Clinton in his limo at the road gates just out here. Nobody actually told us that they was in the area, and I actually had the phone going in the cabin within a minute or two of starting the bridge with Scotland Yard on the line, saying, "Can you close the bridge please, we've got the President waiting." But that was too late, I'd started by then, the boat was starting to come through.
Today, the massive bascules of Tower Bridge are raised on average less than twice a day. The ocean-going freighters of old have long given way to tall-masted yachts and pleasure boats entering the upper pool. But Tower Bridge still shines as the proud portal to the City of London, a testament to technical ingenuity and the glory of a bygone era. It welcomes all who arrive here, be it by ship or by tour bus.
The original London Bridge was quite a remarkable bridge, and it went through a whole range of evolutionary stages, from being just a plain road bridge to then having houses built on it. It had a chapel built on it. It had a gatehouse. The bridge didn't have a regular pattern of arches. It was very irregular. And the reason it was irregular is when they built it, they built the piers on parts of the riverbed that were hard. They poked the bottom with large poles, and where it was solid, they built a pier.
It acted actually as a Thames barrier. It was such an obstruction to the river that at all states of the tide there was a 4 to 5 foot difference in level across the bridge.
The drop in water level created by the bridge made it virtually impossible to go upstream, even for boats small enough to pass through the narrow arches. And even going with the current was a risky undertaking that became known as shooting the bridge. For 6 centuries, London Bridge remained the only way to cross the Thames other than by boat or ferry. At the dawn of the industrial age, trade boomed in London. England was becoming a major colonial power with territories and trade interests around the world, and an increasing flow of goods arriving at her ports. Beginning in 1729, a number of new bridges were erected in London and neighboring communities, but all were west or upstream of London Bridge. In the early 19th century, London's population passed the million mark. It would quadruple within 50 years, making London 4 times as populous as Paris or New York City. In 1831, a new London Bridge was completed right next to its crumbling predecessor, which was torn down after the new crossing was taken into service. The new bridge did little to ease congestion.
There was, of course, no other bridge to the east of London Bridge, and to the east is where a lot of the city was starting to grow, so that more than 1 million people lived to the east of London Bridge, and that was the only way that they could cross the river. So it was jam-packed full of horses and carts and people and hand carts and animals all being driven across. So there was a real desperate need to have some other river crossing.
Though the need for a crossing east of London Bridge was obvious, building another bridge seemed out of the question. Because to the east of London Bridge began what is called the Pool of London, an undistinguished stretch of river barely 1.5 miles long. Today, the few remaining warehouses that line the Pool of London house loft apartments for affluent Londoners. In the 1800s, they were at the center of the world's busiest port, with a turnover of up to 300,000 tons of goods per week. At times, more than 20,000 workers were employed on the docks and wharves.
If you ever see the photographs of the upper pool of London with all the ships in it, you could almost walk across the river on the shipping. There was that many ships in the upper pool.
Trade companies that had invested large sums in the docks were among the strongest opponents of a bridge to the east.
To have built an ordinary bridge across the...
So the two coming together are much more than the sum of the parts, and this is what gives this great bridge landmark quality.
Tower Bridge was called the Wonder Bridge because of the way it was automated and opened to let ships pass through.
It's only when you see the machinery and you understand how it worked that you appreciate the enormity of what it was for the people that designed it in the 1890s.
Although more than 100 years old, Tower Bridge is a relative newcomer among London's bridges. The history of bridging the Thames goes back almost 2,000 years. Invading Roman armies constructed the first timber bridge near their settlement Londinium around 70 AD. In 1176, construction began on the first stone bridge across the Thames. It would be the city's most famous landmark for centuries, London Bridge. Completed in 1209, the long-awaited bridge quickly became popular, not only as a means to cross the river, but as a place to do business, even as a place to live. In today's cultural and architectural landscapes dominated by rapid change and globalization, there are a handful of monuments and buildings that stand out. They have acquired a status that goes beyond their mere form or purpose. They have become the symbols for their cities, their time, their cultures. Its long history has awarded the City of London many remarkable structures. But together with Big Ben, the famous clock tower flanking the Houses of Parliament, the most recognized symbol for this city is the Tower Bridge. Revered by Londoners, loved by tourists, the bridge on the eastern end of London's inner city is perhaps the most photographed bridge in the world.
Tower Bridge is a combination of marvellous feats of engineering with a magnificent, monumental Victorian architectural structure.